Imagine this scenario. A signal comes from the outskirts of the solar system. Not an image, not a photograph, only numbers, slight deviations in trajectories, a discrepancy in where the object is supposed to be. The data points to something with the mass of the sun, compressed into a sphere the size of a city. No light, no tail, no flare. And for now, the question isn't, what is it? The question is, what happens to a planetary system when such an object passes through it? Today we're going to dive into a controlled timeline, a hypothetical scenario based on real physics. What could a silent neutron star, a pulsar, or a magnetar bring with it, besides its extreme physical properties and behavior? So in the cold depths beyond Pluto, something begins to stir. At first, it's nothing more than a faint gravitational ripple. Kuiper belt objects drifting off course. Long-period comets knocked from their ancient orbits. Astronomers notice slight anomalies in the trajectories of probes and in Neptune's orbit, hinting that a colossal visitor is hiding in the black abyss. The interstellar void, usually silent, now sends a message. A super-dense object is approaching. From the heights of Mauna Kea and from the depths of the Antarctic ice, telescopes and neutrino detectors pick up echoes of something unusual. The distortion of starlight indicates intense gravity bending it, a fleeting shimmer when background stars briefly brighten and warp. At that moment, the invisible becomes undeniable. Something unimaginably massive is rushing into our cosmic neighborhood. Through the hiss of static, radio telescopes catch an eerie signal from the void. Uncertainty spreads. In hushed voices, scientists begin to realize that the calm routine of the solar system, which has lasted for 4.5 billion years, is about to be disrupted. We have an uninvited guest. But what is it? While the object is still far away, researchers try to determine its nature. It is small in size, yet quite significant in its impact. However, the models don't start with an image, they start with a mass. Scientists are betting that it's a neutron star. A neutron star is what remains after a core collapse supernova compresses a star's core so much that it exceeds the limits of normal matter. A mass comparable to the sun's is compressed into a sphere about 7 miles in diameter. This scale determines everything that will happen next. The surface gravity is extremely high. The escape velocity from its gravitational field is a significant fraction of the speed of light. In turn, the density is so great that solid and liquid cease to behave like ordinary states of matter. Nevertheless, a single compact object can present 3 different threat profiles, 3 personalities, depending on its rotation and magnetism. The first is a quiet neutron star. Here, gravity dominates. It emits little light, sometimes detectable mainly by its motion and faint thermal radiation. A typical example is RxJ 1856, an isolated neutron star, visible primarily because it's nearby and still warm enough to glow faintly in X-rays. The second variant is a pulsar. Here we have gravity plus a stream of particles and beams like those from a lighthouse. Rapid rotation and strong magnetic fields create focused radiation. An extreme example of such phenomena is PSR J0952. This pulsar spins at an incredible rate of 707 revolutions per second. For classic behavior, the benchmark is the Vela pulsar. It has regular pulses. At a more modern rate of 11.2 revolutions per second, high-energy radiation, and a bright surrounding nebula visible in multiple wavelengths. The third possibility is a magnetar. Here we have gravity plus an ultra-strong magnetic field, with the risk of flares caused by crustal stress and magnetic reconfiguration. An example of such an object is the soft gamma repeater SGR 1806, which in 2004 produced a giant flare, powerful enough to affect the ionosphere here on Earth, despite the unimaginable distance. The same size class, the same basic remnant material, different ways of releasing energy into space. The proposed scenario is built on these figures: mass, distance, orientation, and activity, because they are what will determine whether it is primarily a gravitational disturbance, a radiation issue, or a magnetic problem. By the time the uninvited guest crosses the outer planet's boundary, everyone will already know that something is there. Right now it's moving through the Kuiper belt, roughly 30 to 50 astronomical units from the Sun, beyond Neptune's orbit. Even at this extreme distance, the gravity of the neutron star begins to affect the structure of our solar system. Pluto and its moons show unexpected deviations from predicted orbits. NASA's New Horizons probe, passing through the Kuiper belt, records slight unplanned course deviations, as if pulled by an invisible hand. Astronomers finally get a faint image of the object. It appears as a dark point, eclipsing background stars as it drifts, a characteristic gravitational lensing effect. The object itself remains nearly black to our eyes, emitting little or no visible light, but as it approaches the 30 AU mark, sensitive infrared telescopes detect a faint glow. This could be surface heat. Though the neutron star is dead, it may still be hot, possibly heated to hundreds of thousands of degrees. However, with such a tiny surface area, it appears almost imperceptible. Now it looks like a ghostly ember against the void, detectable only with our best instruments. And while sunlight is weak out here, the neutron star begins to bring its own. Charged particles captured by its powerful magnetic field start to spiral around it, possibly emitting faint X-rays. NASA's orbital X-ray observatories suddenly register bursts of X-ray photons from an apparently empty patch of sky. Could this be the result of our intruder exciting the rarefied gas of interplanetary space? It is possible. The heliosphere, the bubble of solar wind around our system, begins to collide with the neutron star's magnetosphere. A shock wave forms, similar to the bow splash of a ship in water, but here it is solar plasma hitting the approaching object's magnetic field. And meanwhile, back on Earth, the public becomes aware. At first there were leaks and rumors and science blogs, but now it's headline news. A dark star is approaching. In these early days, the focus is on predictions. Observatories around the world cooperate to refine the intruder's trajectory. Will it pass at a safe distance or pose a direct threat? Orbital calculations converge. This neutron star is not on a collision course with Sun or Earth, a small relief, but it is approaching an uncomfortably close distance in cosmic terms. The estimated flyby distance on the order of a few astronomical units. In fact, it seems likely to pass through the solar system, possibly between Saturn's and Jupiter's orbits, before veering away. Everyone holds their breath. It is close enough to disrupt everything. Even at the edge of the solar system, the consequences are already making themselves felt. Long-period comets from the Oort cloud, a spherical shell around us containing trillions of icy bodies nearly a light year away, begin falling inward under the influence of a distant gravitational nudge. Over years or millennia, some of them may have reached the inner solar system, serving as a delayed harbinger of this flyby. This scenario is reminiscent of the story of Schultz's star. a red dwarf that passed near our Oort cloud 70,000 years ago, likely disturbing comets that will only arrive here 1 million years later. The view through a telescope is both breathtaking and terrifying. A tiny, dense object, essentially an atomic nucleus the size of a city, enters the zone where our giant planets reside. The outer part of the solar system is about to encounter a stellar ghost. Jupiter is the first planet to truly feel the power of the intruder. As the neutron star begins to cross the inner space of the giant planets, possibly at a distance of 10 to 15 astronomical units, balance of forces in our solar system's gravity starts to shift. Astronomers measure changes in Jupiter's motion. The gas giant deviates by several thousand miles from its expected course. Saturn's elegant ring symmetry shows strange ripples. These concentric bands of ice and rock begin to precess under the influence of the changing gravitational field. And although the Cassini probe can no longer observe this, radio telescopes on Earth detect unusual clumps in the rings, growing over the course of several weeks. The orbits of Saturn's moons also change. Titan, a world with its own dense atmosphere, shows a slight increase in orbital eccentricity, as if nudged by a massive hand. The neutron star rushes inward at several hundred miles per second. As it approaches the 5 AU mark, roughly Jupiter's orbit, its immense gravity wreaks havoc. Gravitational tides begin to affect the planets. Tides in space are usually weak, but here we have two objects with solar mass, the Sun and the neutron star, now pulling the planets in different directions. Jupiter's liquid interior core begins to churn under the enhanced tidal forces. On the gas giant's cloud tops, new storm systems spontaneously form. The Great Red Spot deforms, and new red storms appear as if Jupiter is battling an invisible opponent. We watch in awe as the orderly behavior of the moons is disrupted. Some of the smaller outer moons of Jupiter and Saturn are completely ejected from their orbits, becoming orphans. Others suffer a more violent fate. Telescopes capture bright flashes as small moons around Saturn collide with each other after their orbits are destabilized. Meanwhile, if the neutron star is a pulsar, by now its effects are not limited to gravity alone. We could be experiencing radiation bursts. Each time its beam crosses the line of sight to Earth, detectors register spikes. Imagine a cosmic lighthouse now flooding the inner solar system every few seconds with pulses of X-ray and gamma radiation. When the beam hits, spacecraft instruments can become overloaded. Astronomers may need to shut down sensors to protect them. Even the planets themselves feel the cosmic lighthouse effect. Nights on Jupiter are periodically illuminated by X-ray auras as the pulsar's beam energizes its magnetic field. And if it is a magnetar, then we're truly hoping it isn't. At a distance of 5 astronomical units, the magnetic field of such an object, though weakened by distance, can begin to induce noticeable currents in conductive materials. Jupiter and Saturn, with their metallic hydrogen interiors and strong magnetic fields, could act like antennas. Radio bursts and auras far more intense than any ever recorded may appear, driven by the magnetic influence of the intruder. NASA's Juno spacecraft orbiting Jupiter records strange readings as Jupiter's magnetosphere is compressed and deformed by the field lines of a new star. Saturn's graceful auroras may turn into wild flickering halos over its poles. Amid these turbulent changes, one trend becomes clear. The neutron star is moving toward the point that brings it closest to the Sun, which lies within the asteroid belt. Next in line are the inner planets. Humanity braces for the approaching storm, watching wide-eyed as the giant has already caused upheaval. The warning from the outer system is stark. The old gravitational order is collapsing, and now the fate of the inner worlds hangs by a thread. As the neutron star burst into the inner solar system, crossing the asteroid belt, the small rocky planets enter the zone of direct danger. Here the consequences become immediately tangible for us on Earth. The first sign is a change in the sky itself. Even before the gravitational effects reach Earth, we'll witness a strange spectacle. The light of the stars and the sun will be deflected by the neutron star's gravity. At dawn and dusk, a faint second glimmer of sunlight will appear in the sky. An echo of sunlight focused through the intruder's gravitational lens. It will look like a shimmering halo or a sun mirage, hovering at an unusual time of day. Next comes orbital distortion. Mars, being farther from Earth, is the first to feel the intruding object's influence. The orbit of the red planet, once nearly a perfect ellipse, stretches into a more eccentric shape. From Earth, Mars' position begins to deviate significantly from predictions, first by minutes, then by several hours of arc. For Earth, this event is even more harrowing. In the bright daylight, some observers report seeing a strange point, surrounded by a dim halo, moving across the sky. It is not a solar eclipse caused by the moon, but a neutron star passing near the sun from our perspective, bending sunlight around itself. This is a gravitational lens effect, essentially an Einstein ring. Gravitationally, Earth's orbit is now changing. The neutron star passes by without striking us, but pulls at an angle that the sun's gravity cannot fully counteract. Earth's orbit tilts by several degrees from its previous plane, like a spinning top knocked off balance. A year may lengthen or shorten by several days. Seasons, determined by Earth's orbit and axial tilt, begin to shift unpredictably. The immediate consequences for Earth itself will be dramatic. Tidal forces from the neutron star will generate unprecedented tides in our oceans. Remember, this object has roughly the same mass as the Sun, and at closest approach, it is at a distance equal to a fraction of the distance between the Earth and Sun. For a time, Earth will find itself in a kind of tug-of-war between two stars. As the intruding object passes by, the difference in gravity between the side of the Earth nearest the neutron star and the far side creates a tidal bulge far larger than any caused by our moon. Coastal cities face super tides. Some harbors are completely drained and then flooded again within hours. Elsewhere, the sea rises miles inland. Along fault lines, the solid Earth experiences tidal stresses. Minor earthquakes become frequent as the crust deforms in unusual ways. In some cases, this stress triggers strong jolts and volcanic activity. A number of volcanoes in Indonesia, dormant for decades, awaken simultaneously as the passing gravitational field affects their magma reservoirs. If our intruder is a magnetar or a pulsar, Earth's magnetosphere and atmosphere face even more unique effects. The magnetosphere compresses and quivers. A bright polar storm engulfs the entire globe. Night turns to day in surreal neon waves as charged particles from the sun and the neutron star's winds cascade across our sky. This is not a gentle polar aurora, typical of normal solar activity. It is a storm covering the entire sky. Power grids, already stressed by induced currents, flicker and in some places fall under the onslaught of geomagnetic phenomena. Low Earth orbit satellites spiral unpredictably as atmospheric drag increases due to energy injected into the upper layers of our atmosphere. Radiation also becomes an issue. If it is a pulsar with a beam sweeping across Earth, periodic bursts of intense radiation interrupt day and night. Our atmosphere and magnetic field protect us from the worst, but satellites and unshielded astronauts receive high doses. Space agencies rush to shelter ISS crews in protected zones. Fortunately, the pulses are brief, lasting only a few seconds. And Earth's rotation combined with the neutron star's trajectory means the beam does not linger on us. Meanwhile, during the closest approach, in addition to the gravitational lensing near the Sun, people worldwide notice a strange phenomenon in the sky. Daylight will dim oddly, at moments unrelated to cloud cover. This is partly because the neutron star briefly channels and redistributes sunlight through its lens, and partly due to a slight change in Earth's distance from the Sun. Then, over the course of several weeks or even days, the direct interaction ends. The neutron star, moving at incredible speed, has now passed Earth and is heading toward perihelion, its closest point to the Sun. The inner planets were affected but not destroyed. Earth still orbits the Sun, albeit along a slightly altered path. Life on Earth has been shaken by floods and earthquakes and a cosmic light show. Yet humanity survives, watching the departing intruder with a mix of fear and relief. The immediate danger has passed, but the consequences are just beginning. The planets now have new orbits. Swarms of asteroids and comets have been displaced. Earth has suffered from natural disasters and infrastructure stress. Observatories sift through terabytes of records, gravity readings, magnometer logs, telescope images, and spectra. In essence, humanity is taking inventory of the entire solar system, checking planets, moons, and rings for their new positions and states. A brief summary emerges. All 8 planets remain intact and bound to the Sun, but many have shifted slightly in their orbits. Hundreds of asteroids have been thrown onto new trajectories. Space agencies flag some of them as potentially hazardous to Earth. Comets from the distant Oort cloud are indeed moving closer, though they will only arrive millennia from now. Such an intrusion is not just a thought experiment. A dim binary star nicknamed Scholz's star most likely passed about 0.8 light-years, or 52,000 astronomical units, from the Sun around 70,000 years ago, disturbing our outer cometary reservoir. And the star Gliese 710, according to predictions based on its trajectory measured by Gaia, will pass through the Oort cloud in roughly 1.3 million years. We now intuitively understand that the solar system does not exist in isolation. The galaxy can send visitors our way, no matter how rarely. Are we ready for this?